Okay, now we need to expand the idea. We've talked about the theory, the theory being primarily the Hardy-Weinberg, and we're going to try to use the Hardy-Weinberg a little bit. So we've calculated allele frequencies, all right? That's what we did in the last one. And now we're going to use those allele frequencies to kind of look at how we might use the Hardy-Weinberg. It's three of the big uses besides just pure theory and developing theory, which is wonderful, but to actually apply it, you can test for a change in gene pool. In other words, has anything happened to that gene pool over time? If it has, then you can go look at, well, okay, now we got to figure out what happened to it. So it's a simple test that we almost always apply when we collect population genetics data, just to see if the loci that we're interested in are in Hardy-Weinberg. Those that aren't are ones that are very interesting to us. You can use it to estimate the number of carriers, so the number of individuals that are heterozygous in a dominant recessive system. Remember when we do those old dominant recessive, we had big A blank. You know, only way we could ever tell what that other little one was the other blank was to do a test cross or whatever. But now we're dealing with population, so we can't test cross everybody. We simply want to estimate the frequency of carriers. And it's very, very important. Excuse me. It's been very important in the areas where we look medical systems, where we're trying to think about how frequently this rare disease might be out there and what's your probability of having it. So genetic counseling uses this basic approach. It's been modernized, a little fancier than what we're going to do, but basic approach to kind of estimate, okay, in a normal population, this is your chance of having, being a carrier for this. And here, now based on your pedigree, it changes to this probability, etc. And then obviously you can use it to model these mechanisms of gene pool change. And that's where we'll go to in the next series of lectures. But in this one, we're going to look first, develop a test for a gene pool and show you an example. And then we're also going to do one for a couple of them for these carriers, just to show you how that might work, because these are common problems, right? So let's test for a change in gene pool. So first we need a gene pool, all right? So here are the basic rules that you work from the gene pool. First, you have to figure out the allele frequencies for however many alleles you have. We're going to do this with a system where we can see the codominants and all that. So we're going to do allele counting. We then need to figure out expected genotypic frequencies, okay? We're not going to deal with ratios. We're not trying to figure out 9, 3, 3, 1 or 3, 1 or that. We're going to figure out the Hardy-Weinberg ratios. We're going to do this by entering the allele frequencies in the Hardy-Weinberg equation. So we figure out P, put it in and square it, figure out Q, put it in and square it, and then 2 times P. Those will give those, okay? Now, ultimately, what we're going to do is do a chi-squared test. That's the classic test we use for testing Hardy-Weinberg. For chi-squared, remember, you need observed and expected. Well, here we're going to get our expecteds by multiplying these expected genotypic frequencies by the total observed counts. I'll show you how to do that in a moment. It's a lot simpler than it is in writing. Okay, and then we just complete the chi-squared equation. The only real difference here is that we're going to use, for our degrees of freedom for that table value, we're going to use n minus 2. Remember when we did the simple test with ratios back in transmission genetics, it was always n minus 1. So if you had 3 groups, it was just 2 degrees of freedom. Here it's going to be n minus 2. The reason for that is you always lose 1 for doing the test, right? That's one of the degrees of freedom. The second one is that you're estimating the genotypic frequencies, or estimating the alleles frequencies from the raw data. So you actually lose 1 for that, which then in turn lets you build your genotypic frequencies. All right, let's take a little example. This is the Chiricahua Mountains in New Mexico, beautiful area. There's a fly there, like fruit fly relative. This goes back many, many years, where people could actually look at some variants of these flies, and they went out and they collected them. They collected eggs from the females, and in the eggs they observed there were two different allelic forms, standard and the Chiricahua form, and they noticed that in the standard forms they had 41 eggs, they got 82, and of the heterozygous eggs they could determine heterozygotes, and then they got 27 of the homozygous for the Chiricahua form, pure Chiricahua in the eggs. So the question is, are these in Hardy-Weinberg? Well, first thing you have to do is you have to do the allele frequencies. We've got 2 alleles, an S and a C. Pick one of them, doesn't matter. We'll just pick frequency of S here, and we'll call it P, right? And we say, okay, we've got 41 here times 2, right? Plus 82 of the hets, right? Divided by whatever the total is times 2, which is 150 times 2. And we get a frequency of about 0.55, okay? Probably round that down a little bit, so 0.55. All right, well, remember that P plus Q is equal to 1, so P is equal to 1 minus Q, Q is equal to 1 minus P. So we want to know Q in this case, right? So we want to take 1 minus 0.55, whatever, and it gets 0.453. So now we have the frequency of our two alleles, one frequency and there's another. We should be able to fill in the Hardy-Weinberg. Sure enough, we can take this first one, right? We square it, that's part of the Hardy-Weinberg. Then we say 2 times P times Q, the frequency of the S allele and the C allele will give us our expected genotypic proportions for the hets, and the expected genotypic proportions for the homozygous for the Chiricahwas is just 0.453 squared. Now, because we're doing Hardy-Weinberg and we're doing a chi-squared, we need to get some expected counts. So we just multiply these by the total and each one of these, and when we do that, we expect to see somewhere around 44.8. Remember, you don't have to worry in chi-squared that you can't have a eighth of an egg, okay, or something, 0.8 of an egg. You just take it as a number, it's just math. So we expect about 44.8 here, about 74 here, and about 31 or so here, okay? Well, those aren't exactly that. That's not 31, that's not 74. How close are we? Well, we do the chi-squared test, right? We just take the observed up here minus the expected, observed minus the expected, observed minus the expected, square each of those, divide each of them by the expected. We expected 44.8 for this group, 74.4 for this group, and 30.8 for this group. When I do that, I get an observed chi-square of about 1.57, right? My table value, because remember we're subtracting n minus 2, so there's 1, 2, 3 things here. So 3 minus 2 is 1. 1 degree of freedom is 3.84. We compare this observed versus this table. The observed is much smaller than the table, so we would fail to reject Hardy-Weinberg. So what we basically said is, went out and caught some eggs, and they were not perfect, but they were certainly very close to being in Hardy-Weinberg. So we're failed to reject the idea. There's no reason to think there's any departure from Hardy-Weinberg. All right. Then they went and they got adults, and they said, okay, let's figure out the same thing in these adults. And when they did, obviously have a different count, not 150 anymore, but they did the same exact thing. Calculated the frequency of the S allele, 2 times 57 plus 169 divided by 2 times the total, gives us 0.555. 1 minus that is 0.445. So for our purposes, 0.55, 0.545. And these were the numbers we had for the eggs, and they're just spot on. I mean, within rounding error and other things, those are no difference. So allele frequencies are exactly the same in the eggs as they were in the adults. All right. So, but is this still in Hardy-Weinberg up here? Is that true for genotypes? So we have to fill in the Hardy-Weinberg. So now we just take the new values and fill them in. So we got those, multiply times the total, which at this time is 255. We end up with an expected of 78.5. Well, that's much smaller. We expected a lot more than we got. We seem to here expected a lot more than we actually have, but here we got a lot more than we expected. So maybe this is, we'll see whether this works out or not. Observe minus expected, observe minus expected, observe minus expected, square each of those units, divide by the expected. So for the first one, it's 78.5. For this one, we'll divide by 126, and this one divide by 50.5, and we come out with 29.7, a very large departure. Again, our expected value, table value, is just 3.84. So our observed value is much, much greater than what we expected it to be. It's way off. So we would reject. The adults are not in Hardy-Weinberg. So quite interestingly, what we're seeing here is that the eggs were fine. They were completely in Hardy-Weinberg. But by the time the eggs matured to adults, apparently being homozygotes were not really a good idea. We see an increase in the heterozygous proportion. Okay, they didn't convert. These didn't suddenly become hets. What happened is that these guys, these homozygotes, disappeared. That's the argument. Okay, so we saw an increase over what we expected in the heterozygotes and a decrease simultaneously in both of the homozygotes, and the allele frequencies didn't change. Right, so we lost these equally at their proportions. This is what's a classic case of what is known as heterozygote advantage. In some populations, it's better to have both alleles there functioning, both mutations functioning, makes you a better system than it does to be one or the other in a pure form. I worked on fish in small fishes in Texas below a dam. It was a hypolimnion dam, so it was cool water, and it would release water for when they needed power generation. So you'd have this flood of cool water relative. Imagine in Texas when it's 120 degrees, 115, and this cool burst of water comes through, and then it would warm up, right? They would shut down for the night or the next day, wouldn't run it for a few days. So you had this weird cycle where if you were a kilometer or so down from the dam, because right at the dam is always leaking, as they call it leaking, but it was always water coming out, it was cool, but it would heat up as it went down a kilometer or two in the Texas sun. And then suddenly this flush of cold water would come. So the fish are sitting there in this environment that was just going up and down temperature-wise. It turned out that was a great place to be ahead. If you were right at the dam, they tended to be more fish that were genotyped homozygous for alleles that worked with cold water, way far down, 10 kilometers down. You wanted to be a fish that could function in warm water. And then here, this fluctuating part, you wanted to be heterozygotes. So it actually does work that way, and that's the way how we would see the system. Okay. Well, the second thing I wanted to do in this lecture is talk about how might you use these if you were genetic counseling, or if you just happen to have a dominant recessive trait you want to work with. Well, here you estimate, again, just ignore the words estimate here, but you can estimate the frequency. And so here's a simple little example. We sampled 400 individuals. We see that 300 are some dominant type, and we want to know how many hits we have. In humans, we often call these carriers because they're hiding a particular genetic trait or disease, right? They're carrying it. So what do? Well, A is simply dominant over little a. That's no big deal. Okay, we've got 400 total, 300 are dominant. Must mean that 100 are recessive. Simple math, right? 100 divided by 400 gives me 0.25. And what is that? That's Q squared. That's the frequency of my heterozygotes, right? Excuse me, my homozygous recessives in this population. So that's Q squared. I just did it by simple math. That's my best math number. All right. Well, here I've got to get down to Q, but if I've got a squared value, I can just take the square root and get the Q. So if I take the square root of 0.25, remember numbers between 1 and 0, when you square root them, go up. When you square them, they go down. It turns out to be 0.5. Okay. Now I know Q. I bet I can figure out P by some simple algebra, right? 1 minus Q is P. So in my case, 1 minus 0.5 is 0.5. So now I know P and I know Q. I ought to be able to put those together, multiply times the total, and I can tell you how many heterozygotes I have, how many carriers. So I would expect out of this 400 total that half of them are actually heterozygous. Simple way to do it. We just figure out what the number of recessives are, figure out what that proportion is. That equals to Q squared. Take a square root. That gives me Q. Do a little back math. Well, I did this one time myself. I love trains. I was sitting in a small train station out in south of Canterbury in the UK, and a train wasn't coming by for a while, and I started looking around. There was a newspaper sitting on the bench, so I picked it up and I started reading through it, and I noticed that there was a little article, tiny little article toward the back on a genetic defect. And this genetic defect turned out to be a deletion of a section of a gene. So this is one of those deletional mutations, right? But it was just a simple mutation where you'd had a micro deletion out of a gene. Okay, which resulted in a protein that had a slightly different function. And what they gave me were some statistics. So I was sitting on my little pencil and I went, okay. And being sort of a genetics geek, I sat down and went, wonder what I can do with this. Well, it turned out to be a human mutation, a mutation in humans. And the system said about 1 in 100 humans sampled in the population they sampled were homozygous for these mutants. Okay. So I said, wow, that's kind of weird. I wonder how many carriers there are. All right. Well, I said, they're homozygous. It's a mutant. It's a recessive, okay, mutant. So what that tells me is that 1 in 100 equals Q squared. Looks like we're going to do the same thing we did before, right? If you want to take that and do it in a calculator, I did it with fractions, but you could do it with a calculator. It's 0.01, right? That would be the same thing as 1/100th. Take the square root of that. Now remember, you take the square root of things between 1 and 0, they're going to go up, right? So it turns out that Q is equal to 0.1, so 10%, right? About 0.1, about 10%. So 100 minus 100% minus 10%, or 1 minus 0.1 is 90%, gives me P. Very simply now, I know P, I know Q. I can figure out how many carriers. 2 times P times Q tells me I've got something like about 18% of my individuals ought to be carriers. So this sample of 100, I'd have around 18 individuals that would be carriers. Okay, they wouldn't have this full, whatever the mutation is producing, the gene that they have is going to function differently, but they could potentially produce children that were homozygous for it, depending on a simple Mendelian type cross. Okay, now what was interesting about the article was this was the protein that was the mutation was in was a docking protein for HIV. And what was happening is that HIV was coming in, but it wasn't able to connect to this. There was a mutation in the protein that it used to latch on to the cell itself and be transferred in so they could sort of take over and start reproducing itself. But the virus couldn't latch on. So these were individuals, these 1 in 100 that were homozygous, while they had this mutation, which didn't have any other effect on them at all. But if they got into the environment where there was HIV, they were essentially protected, at least the form they were looking at of HIV. The data were from people that were in high exposure, high risk of HIV exposure. So they were in the sex trades, or they were intravenous drug users, or something like that. Okay, but what I wanted to point out to you, besides the fact that they're 1 in 100 people could be involved and not worry about getting this form of HIV, get lots of other bad things, but they could form there, is this relationship. This is only right here, right? 1 in 100 individuals are homozygotes, yet 18 times the number that are homozygotes are actually carriers. And this is very true. If we go and we look at basically point mutations or other type of genetic diseases that we think of as allelic forms, they're often very, very rare. Like 1 in 2,000, 1 in 5,000. So we're talking about 0.0000 something. Okay, very few people have them. Where they're going to be stored, and the ones that are important are the carriers, or these individuals, right? And that's why genetic counseling goes out and tries to figure out what's your probability of being a carrier, because you won't have the disease, but you could pass it on to your children, and it's based on the frequency of that particular disease, the genetic disease in the population. Right? So just a kind of a nice little way to look at it, inform, and nice little calculation that we can do. All right, so we've done now in this, we've figured out little frequencies in the last lecture. This time we figured out a couple of ways that we would use the Hardy-Weinberg. One time when we know all the genotypes, one when we don't, but we want to estimate them. Okay, and you certainly could estimate homozygotes from this too, right? Just by taking P and squaring it. Okay. Now what we want to do is we'll start on that third thing for this. We want to start walking our way through all of these mechanisms that might impact a gene pool and see what Hardy-Weinberg says about that.